Can the limit of the extremal point process be recovered in either case? Yes. So this is actually the setting that we are working with right now. So instead of writing bazillion papers on on the maxima, we decided once we understand the structure of the maxima, we just write down one paper for the point process, and then you can recover the limit theorem for the case r greater than 2/3.
So I think maybe it's a good time to continue with Sam Johnston's lectures.
So I'm just starting a new stream on YouTube. We should be live now, so and we can start the cloud recording.
Okay, should I share my screen?
Yes.
Is everyone looking at my screen now?
I see your screen, yes.
Yes.
Okay.
Yeah, this works out. Very good.
Okay, so I'm going to be talking about the extremal particles of branching Brownian motion. So presumably we've all seen branching Brownian motion before, but just to fix the exact model we're working with, I'm going to be talking about binary branching Brownian motion where particles have unit exponential lifetimes. So particles move around like Brownian motions, and after an exponential amount of time, they die and they're replaced by two particles that inherit the spatial position of their parent. So as time progresses, we have more and more particles in the system, and we're going to be most interested in the extremal particles. And the extremal particles, that's an informal definition for the particles that are the highest up in the process at time t, particles that are furthest away from the origin in the positive direction. So this talk is just going to be an overview. I'm not going to prove anything. It'll be centered on three questions we'll ask about these extremal particles. So the first question we'll ask about the extremal particles, and the most natural one to ask is, where are they? So at a large time t, roughly where are the particles that are furthest away from the origin in the positive direction? And once we've understood that question, we'll move on to another interesting question, which is if the particles are at a certain, if the particles that are furthest away from the origin lie at a certain height, we're interested in how did they get there. And I have to say, before I knew the answer to this question, I had absolutely no clue what the answer would look like. It's difficult to guess whether this past blue trajectory might look like a straight line until quite recently. And then, can people see my cursor, by the way?
Yes.
Yes.
Right. It's difficult to guess whether the trajectory of the particle that ends up at the highest position, does it hover around the origin and then suddenly burst up at the very end? Or does it look more or less like a straight line? So that's the second question, how did they get there? And the third question we'll ask is, are they closely related? So if we pick some of these particles that are among the highest particles at a large time t, is it the case that they are both up there because they had an ancestor that lived very recently and this ancestor got to a really high position? And they're both descendants of this common ancestor that last existed near time t? Or is the opposite true, that actually it's a coincidence that they're both so high up and they're totally unrelated? There are just loads of particles in the system and lots of them end up at this high height, and it's a coincidence. So those are the three questions we'll ask. So I should first a disclaimer that I'm going to import lots of results from branching random walks and just pretend that the paper was talking about branching Brownian motion. And I won't always be so precise in the statements of the results. And whenever I say t, t is a huge time. Okay, so the first question. We want to work out where the particles that are, the highest particles are at large time t. And in order to do this, or just get a rough grip on the question, we need to first understand how many particles there are at time t. So if NT is the number of particles alive, then NT grows exponentially, at least in terms of expectation. And in fact, if you look at the ratio of NT with its expectation, it behaves really well. So if in this first graph here, I've plotted NT against time, and in the second graph, I've divided NT by this exponential growth. And you'll see that as time goes to infinity, this ratio sort of stabilizes. The height where it does stabilize is random, but it stabilizes. And actually, it turns out that the height at which it stabilizes is exponentially distributed with mean 1. So the take home of this slide is that at a large time t, there really are roughly e to the t particles alive. So we know that there are roughly e to the t particles alive. So we'll be interested in calculating the expected number of particles that lie above a certain height at time t. And thanks to the many-to-one formula, the expected number of particles above a height y at time t is exactly equal to the total expected number of particles times by the probability that, you know, a typical particle ended up above y. So we have this nice formula here. And of course, since the expectation of the number of particles alive is e to the t, we have this term, and this integral corresponds to the probability that Brownian motion ends up above a height y at time t. So this quantity here is decreasing in y, and we want to choose y that's big enough so that this integral gets small and it competes with this huge e to the t term. So we want to choose y big enough so that this quantity has order roughly 1. And it's a calculation you can do that the right choice of y so that this expected number of particles above y has order 1 is, it's about root 2t minus this funny logarithmic correction. If we chose y any smaller than this level, on average, there would be tons of particles above y. So here's a diagram here of if ft is this special function, this special expectation frontier of root 2t minus the logarithmic correction, then the expected number of particles in a patch above this frontier is tiny. And of course, that guarantees that there are no particles in this patch. However, the expected number of particles in a patch below the frontier is huge. So it's quite natural to guess, at least at a first glance, that if this point is the point where the expectation cuts off, then it might be natural to guess that the highest particles do lie around this root 2t minus this logarithmic correction. However, this guess is wrong, and it's not hugely wrong, but it is slightly wrong. So we have this result by Bramson from the 70s, that if you take a huge time and you look at where the highest particle is at that time, it actually sits at a slightly lower height than we thought it would. So reality doesn't live up to expectations here. Now, we have this higher frontier where the expectation cuts off, but in reality, the highest particles sit a lot lower. So this presents us with something that looks a tiny bit like a paradox, in that we have these two different frontiers, and we know in reality the highest particle usually sits near this lower frontier of root 2t minus this 3/2 root 2 logarithmic correction. But based on our previous calculation using the many-to-one formula, there are on average loads of particles in this patch below the expectation frontier. Now, this seems a bit like a paradox, but of course, when you think about it, it's not. If an eccentric billionaire says, I'm going to give you a 1 in 500 chance to win $1 billion, then both of the following statements are true. You're on average going to win loads of money, and you're not going to win any money very often. So that's what's going on here. On average, there are tons of particles here, but usually there are no particles here. It's a bit strange. And we'll get a lot better understanding of how this happens in the next result by Hu and Shi. So the Hu and Shi result, whereas Bramson's result looked at a large fixed time, and said that usually the particles lie at a certain height. Hu and Chi's result tracks the height of the maximum particle as time goes to infinity. And they find that asymptotically it fluctuates between these. This ratio here fluctuates between two levels. So interestingly, the maximum particle is never below the frontier that was included in Bramson's result. And it's never above the frontier that was given by the expectation calculation. Now, this result just accounts for this weird thing we had before with the ghost particles, where there were loads of particles on average in a patch, but no particles in a patch. Because if we look at this simulation of a branching Brownian motion and we notice that the maximum particle got up to this, it was one of those rare occasions where the maximum particle got up to this higher frontier. Shortly after that period, it has loads of children or descendants in this patch. And for a brief period in time, this patch between these two frontiers is filled with particles. So we have these sort of hidden events that happen very occasionally, where very occasionally you have tons of particles in this gap between the two frontiers. So there's a paper by Matt Roberts, which you can look at, which has quick proofs of both Bramson's result and Hu and Chi's result. So we've answered the first question. The highest particles at time t usually sit at a height around root 2t minus this logarithmic correction. Occasionally they're a bit higher. So we now look at question 2, which is how did these high particles get there? So we know that the highest particle at a large time t usually sits around this height, root 2t minus 3 over 2 root 2 log t. Now, if we trace its path, the path it took back to get there, we get this sort of random trajectory. Now, since every particle in the system itself behaves like a Brownian motion, one natural guess for how it got there, well, a first guess that presumably all of us would think of is, well, maybe it just looked, this path just looks like a Brownian motion conditioned to end up at a height root 2t minus 3 over 2 root 2 log t. So here's the natural first guess. Now, I've been very careful to highlight that this guess is wrong. And let's have a think about why it's wrong. Well, if this were the case, then this process described, a Brownian motion conditioned to end up at this height, would occasionally go above the flat line root 2t, and the order of these fluctuations would be of the size square root of t. But we've already seen in Hu and Chi's result that no one ever goes above this root 2t minus 1 over 2 root 2 log t correction, for large t at least. So this natural first guess can't be exactly right, because if this were true, the particle would occasionally go too high, and we've already stipulated that no particle can ever go that high. So a better guess is the trajectory of a particle. The trajectory of the highest particle looks a bit like a Brownian motion conditioned to end up at that height, but in some sense it respects the frontier. It respects the Hu and Chi result that no particle ever gets too high. Of course, I say it's very easy with hindsight to come up with a better guess of what the result is when you know what the result is. But as I said, I don't think it's easy to guess what the trajectory of this particle is. So indeed, this better guess we have here is correct. And we have this wonderful result by Chen, which was proved in the setting of branching random walks. And I've given a bit of an informal statement here, but Chen's result says that if you look at the trajectory of the highest particle, it looks like a Brownian motion conditioned to end up at that really high height, but also conditioned to never go above this straight line. So the formal way of, the rigorous way of stating this result involves a rescaling of this blue line, looks like a Brownian excursion. So we've answered question 2. We now understand where the highest particles are, which is question 1, and how they got there, which was question 2. So now we move on to looking at the relationships between different high particles. So again, if we pick the 2 highest particles in the system at a large time t, were they likely related very recently, and they had a common ancestor who had a very high position near time t? Or is it a coincidence that they're both there, and actually the common ancestors they share were right at the beginning of the time period? Or could it be the case that something in between is true, like that they were last related somewhere in the middle of the time period 0 to t? And before tackling this question, it's worth mentioning that actually, if we pick not the 2 highest particles, but just 2 typical particles, then it's not obvious when 2 typical particles were last related. So first, let's look at that case. We have this result by Harris, Johnston, Roberts, that if you pick 2 typical particles, so you have at time t, you have e to the t particles, a huge number of particles, and if you pick 2 particles uniformly from the entire population, you don't care about space, and you let pi t uni denote the time of their most recent common ancestor, then it turns out that as this time t goes to infinity, pi t uni surprisingly stays very close to 0. So the vast majority of particles are distantly related, the vast majority of typical particles at least. So and actually we have an explicit formula for this for the limit of this random variable pi t uni. It converges in distribution to a random variable with this strange distribution here. And if you stare at it for long enough, you can check that everything's okay when you plug in s equals 0. I often look at it and get a bit scared. So we now understand how closely related typical particles are, but we return to our original question, which we were interested in, which is how closely related are extreme particles. So one way for setting up this framework is to look at a Gibbs measure. So you choose particles randomly from the population. You choose 2 different particles, but your sampling is going to be biased to e to the beta times the height of the particle. So when beta is positive, clearly you prefer picking particles that are higher up. And as beta gets big, it becomes more and more important to you that you're picking particles that are high up in the system. So we have this very surprising result, I think, by I think it was formulated in the 80s by Derrida and Spon, and proved rigorously by Bouvier and Kofer in the noughties, that if beta is sufficiently big, then when you pick 2 particles according to this e to the beta sampling, then these particles were likely either related right at the beginning or right at the end with high probability. And strangely, asymptotically, both of these events do happen with positive probability. So just to emphasize, it's really unlikely that these 2 particles were related last related at some point in the middle of the interval. It was either O1 from the start or O1 from the end. And actually, there are loads of really interesting papers with this sort of Gibbs sampling. So if you let p beta be the probability that they were related early, and 1 minus p beta be the probability that they were related late, then there's a paper by Chen, Madwul, and Malane, which calculates this probability p beta explicitly. It's given in terms of a Poisson-Dirichlet distribution. And strangely, when this p beta is decreasing in beta, so as beta decreases, sorry, this should say increasing in beta. No, sorry, as beta, it's right. As beta decreases, you get less and less likely to pick particles that are high up in the system. And strangely, when beta is less than 1, p beta is equal to 1. So when beta is less than 1, you do tend to want to pick particles that are high up in the system. But the force of how much you want to pick high particles isn't strong enough to really see any of this late coalescence. And actually you find that when beta is less than 1, all particles sampled, all pairs of particles sampled according to this Gibbs sample with parameter beta, they're very likely to have last been related near the start. There are numerous interesting papers in this direction, like Arguin, Bouvier, Kissler, Madwell, and Pan. Pan has a result which is sort of analogous to the Chen result we saw earlier, where if beta is less than 1 and you pick a particle that's reasonably high up with this e to the beta sampling, then it's a normalization of its trajectory looks like a Brownian excursion. Sorry, a Brownian meander, which is sort of the analog to Chen's Brownian excursion. So that completes the answer to our third question. So just as a recap, we've asked 3 questions about these highest particles. We found that, first of all, the highest particles usually sit near this height with this strange logarithmic correction. And there's this whole story about how the expectation sort of lies to you when you're doing these calculations about where the highest particles are. And there's an explanation for this mysterious phenomenon, thanks to this who and she result, which states that the highest particles do occasionally, very rarely, get a bit higher. And then second, we looked at this, the past trajectories of these highest particles, and found that they did look like a Brownian motion conditioned to end up at this really high height, but there was this repulsion. People in the area often call it entropic repulsion, this mysterious force which is keeping them away from the frontier. And finally, when we looked at how closely related these extremal particles are, we found that it's very likely that they were either related in the very beginning of the process or near the very end of the process. So that concludes the talk. Thank you for listening.
Thank you very much. Can you unmute, Omer? So I should have introduced Sam. So Sam is a postdoc, and this was on the slides. Right now you are in Graz. And are you really back to Graz right now, by the way?
No, I'm in London right now. I got stuck there.
You're still in London? Yeah. Be where you're officially affiliated. But Sam
Sorry,
will...
Nina. Sorry, Nina, I didn't get that.
It can be difficult to be really where you're affiliated.
Yeah, it can.
And this is often the case nowadays.
Yeah, particularly